getting wax lips and the wax bottle. You ever had the wax bottles with the drink inside of them? No, those are old, but basically it's a tiny little, make sure this is going. Yep. It's a tiny little wax bottle. And the wax bottle has, like, it's not juice, it's like a drink in it, like a mixed drink. And like a Crystal Light type thing, but I'm sure it's not light in any way, shape, or form.
Danny,
It's delicious. Yeah.
how long does it take you to prepare it through the slides?
Oh, a very long time. So some of these I've had for a while, but each slideshow probably takes me, I'd say on average, 2 hours. It takes me longer to do the slides than it does to teach the class.
Oh,
Yeah. What's up? Oh, just talking to them. Yeah, so it takes me longer to do the slides than it does to do the class, and then it also takes, like I have to put together the grade book and all of that, the whole binder. Like this isn't so bad because, so the first 2 years I did the class, I wasn't sure how I wanted it formatted. Like everything from the way the binder looked to the pattern of the way we do lessons. It took me a while to figure that out. But now just this year, we're at a point where I've repeated the pattern and the binder setup and everything every year for each course because it's chemistry that I found what I liked.
You just change the syllabus and
so now all I have to do is change the dates and the due dates and then make and change a couple other things. The only thing that is different this time around, I used to test every chapter. And that was just a lot of small tests. But I find that testing every unit is better because it requires you to retain the information for longer. And it allows it, and it's less just constant testing. So the only thing that's different from the last chemistry to this chemistry is the fact that I don't test every single chapter. I test every unit instead. And I do the homework after class. I used to do the homework before class. Now I do it after. But yeah.
Are you, why did you give the Q1 and Q2 packets?
Just because I had them ready.
Oh, you had it ready.
I had them ready, so might as well give them to you, right? And plus, I don't want to give you too much because I didn't want it to be too much paper in your binder. So I'll give when you leave for winter break, for Christmas break, I'll give you the Q4, Q3, Q4 when you go home. So you'll have those. And when you guys come back from fall break, we've only got like 2.
When is fall break?
Next week. I think we have like 2 classes before we get to the end of Q1. And at the end of Q1, I'm going to give you your midterm review packet so you can start working on it.
Midterm review?
Yeah, I have a whole packet for you to do. So you can practice, so you know you can study and you know what's on it and everything.
Last year?
No. No.
Okay.
Yeah, all right, really. I don't know if I believe you, lady.
Are we gonna get donuts like last year, the Tinker Day?
Actually, I'm gonna bring up Tinker Day today. Because the next time you come back to class will be October. So I have to talk about it today. To tell everybody what it is. Oh, you'll learn. We're getting there. It's only the best day of the year.
I think the best day of the year is my birthday.
Oh, that's always
so
true.
they turn 1 year older.
Yeah, and you get presents and you don't have to do anything.
Last year we got donuts and brownies.
Yeah, on the same day. That was crazy. You got brownie points and donuts.
10, right?
Yeah, probably right around there. Yeah.
So are we gonna have donuts again?
Yeah, of course. I'm not gonna let you have a Tinker Day without donuts. Shoot.
What kind of Tinker Day comes on like Friday?
Then it'll be the next Tuesday. Yeah.
Well, this year my birthday's on a weekend, so maybe I'll be able to.
Oh yeah? You can always do it like right after, right? Hey girls, how are you? I got the leggings and the top memo. They're both doing leggings and the top. It's because these are These, like, just have little pockets, but the design is called atomic stained glass. They look like atomic models, but they also kind of look like stained glass. I like it.
Always get something creative.
Nerdy clothes. I love my nerdy clothes. They're so
Remember
fun.
we had a periodic table.
Yeah, I do have one. It says nerdy. Yeah. I do. I have a periodic table t-shirt. I've got 2 different shirts with moles on them. Got my stoichiometry t-shirt. Yeah, I got lots of fun stuff. And goodness knows how many dresses and things. Huh. Go. How was your weekend, girls? You do anything fun? Morning.
I have a that's like that.
Oh, good.
And
night,
I
actually.
it's just like.
Did you make that one, Annabelle?
Yeah.
Yeah?
It says avocado army assemble. It has like a.
I like the avocados. Those are great. The avocados were fun. Avocados.
Doesn't anyone like drawing characters as much as I do?
I'm not good at it, but I mean, I don't mind. You guys like drawing too? I mean, I like to draw, but I'm not real good at it. I'm better at sculpting and crafting than I am with drawing. Now, my grandmother was an artist, like a straight up artist. Actually, she made this little pot right here. And over there, she made that. And over there where you turn in stuff on the counter, there's those lemons in the dish. She made those lemons. And my mom has a couple of her drawings downstairs, paintings.
For those.
No.
Did she make that replica of Commander Tartar?
Where's that? What's that one?
That telephone.
Oh, the telephone? No, that was made by whatever company did the telephone.
Google Commander Tartar and click images.
Okay, I'll have to do that. That one's less a telephone and more an intercom, because these buttons go to certain people's, like within an apartment complex.
Oh.
And you would like buzz into the apartment. This is made by SH Couch and Company. There you go.
Miss Danny, did she literally shape the lemons?
I think, I don't know.
Or did she just paint it?
I don't really know, because that was before I was born, so I don't know how she made it, but she made that. I have a dish in my china cabinet too. It's a tray and it looks like a fish. It's a tray to like put things in, like jewelry or whatever, like little knickknacks, you know.
I don't have a china cabinet.
Hers, it's a fish, but she made scales on the fish by pressing a paper clip into it. It's really cute. It's really cute. I love it. Yeah. If I remember, I'll show it to you later. All right, everybody got your stuff out and ready? Are we ready to go? Yes, ma'am. What's up?
Can we maybe pledge 2 truths, 1 lie?
If we have time. If we have time, we will. But we're gonna have fun today. Today's lab is an easy lab. It's games, basically. You're playing periodic table battleship today. So it's a game. It just the entire point is just to familiarize you with the periodic table, because we're gonna be using it a lot. So it just makes you look at it for an hour, basically, while you're playing a game. All right, so are we ready to start? Let's do it. I have to empty that thing every 2 weeks now, because there's so many of you this time. All right, so studying atoms. So if we go way back in atomic theory to like the beginning of what people thought were elements. Okay, so elements used to be what people called earth, wind, fire, and water. Okay, and this dude is Aristotle. Anybody ever heard of Aristotle?
Yeah,
Old Greek philosopher, right? So-
but Aristotle was a human, not a rat.
Yeah, it's true. So in his time, back in Aristotle's day, people believed that things that we called elements, the elements were earth, wind, fire, and water. Have you ever heard of the elements termed that way as earth, wind, water, fire? Yeah.
Also like light and darkness elements.
Okay, yeah. So that's kind of how that's what we used to say, right? Before we really understood what elements were. So they believed that everything was made up of some combination of earth, wind, fire, and water. All things. Okay. We know now that that's not really true, but that's kind of how they thought of it then. So the next person to come along and propose something about elements was Democritus. Okay, Democritus is old Greek guy, way back when. You can tell by how he's dressed, right? Way back when. So Democritus believed that atoms were uniform, solid, hard, incompressible, and indestructible, and that they moved in infinite numbers through empty space until stopped. What's infinite mean? What's it mean?
It means like you can't even count the numbers. There's just
Yeah.
too much.
Unending numbers, like more than you can count, more than you could ever count. So he believed that they were solid, hard, incompressible, meaning you can't squish them, and indestructible, meaning you can't break them apart. And that there were more of them than we could ever possibly count, infinite numbers, and that they moved around through empty space until they were stopped by something. And he believed that the differences in shape and size determined what? What do you think? Annabelle, do you know?
Number.
Not number, but that's a good guess. Do you know?
The size.
Not size. That's a good guess. So he believed that the properties of matter. So is something shiny? Is something stretchy? Is something brittle? Is something conduct electricity? He believed that all of those properties were due to the shapes of the atoms, and that atoms were these little things that look kind of like this, different shapes, always moving. So Democritus would have said, I shall call these atoms, for atomos, which is a Greek word, means indivisible. Now that's really interesting. The word atom comes from the Greek word atomos, which means indivisible. But guess what we know now? We actually can divide atoms. So their own name doesn't even make sense anymore. But he was onto something, because we didn't know we could divide them until fairly recently in the span of human history. All right, so the next person that made a contribution to this, now we jump way into the future. Look how he's dressed. Way into the future. And we meet this dude, John Dalton. All right, John Dalton had a theory that matter is made up of individual particles. He called them atoms because that's what Democritus had called them. And he said they cannot be what? What do you think?
Destroyed.
Destroyed's a good guess. So yeah, divided or destroyed. He said everything is made up of tiny little particles called atoms that can't be destroyed, can't be divided. I don't know where that came from. So he called it the billiard ball, or people have called it the billiard ball atomic theory. So you know what a billiard ball is, right? Like a pool ball, like he's holding up that 8 ball right there. They're hard. It's a little solid particle. That's how he envisioned atoms. Okay. Yeah.
You think you're getting a cold?
No, I think something's been growing outside. It's making me like this. Whenever if I'm outside for any length of time, I'm like this a couple hours later. And last night I sat outside and ate a snow cone. Now I'm paying for it. So it happens. All right. So billiard ball theory is John Dalton. All right. So then some time goes by and the next person, not too far after him, you can tell by how he's dressed, right? Was this guy, J.J. Thomson. And if you look at the way his name is spelled, usually the last name Thomson is Thompson. There's no P in his name. He's J.J. Thomson. So he had experiments. He's the first one to really do some experiments on this. And he found evidence that atoms are made up of smaller what?
Particles.
There you go, smaller particles. All right. Now he envisioned them as what he called the plum pudding model. Okay, now plum pudding is not something that we Americans really can kind of visualize, but a plum pudding is a cake like that, that's full of prunes, okay, and other fruit. It's called a plum pudding. Do you know that British people call like all desserts puddings for the most part? Like pudding to us is like, chocolate pudding, vanilla pudding, to them a pudding is a dessert. So plum pudding, oh yeah, pudding is anything that's like a dessert is a pudding. So he called it the plum pudding model, but sometimes we call it the chocolate chip cookie model because that makes a little more sense to us Americans because we don't see plum pudding very often. But if you look at a chocolate chip cookie, it's like it's a little body and it's full of other smaller things, right? So he knew that was going on. He knew there was something smaller. So already we have gone, John Dalton, nope, there's smaller things inside that atom, right? So but he didn't know what they were, he just knew they were there. Then next up, we get to this guy, Ernest Rutherford. All right, now Ernest Rutherford was not too far behind, or ahead, I guess, in time's been, from J.J. Thomson. So he found out that all of an atom's positive charge is located in its nucleus. So what do we call that dense, positively charged center of the atom? Everly? Yeah, it's the nucleus, right? All right. So he's the one who came up with this idea. So he's like, all right, I can tell by doing some experiments that the particles that J.J. Thomson found, some of them have a positive charge and some of them have a negative charge. All right, so that they're finding this out. And he's like, well, all of the positive charge is in the middle. So he said, hey guys, atoms have a nucleus. They look kind of more like this. So this is kind of how he envisioned an atom, which is, we're getting closer. Remember, we started with weirdly shaped little particles floating through space that couldn't be divided and moved around till they were stopped and were infinite in number. So we've come a long way. So after him, we get this guy, Niels Bohr. Okay, so Niels Bohr postulates, or basically that's like he hypothesizes, right? That electrons orbit the nucleus at fixed energy levels. So orbits further from the nucleus have highest energy levels. And when electrons return to a lower level of energy, they emit energy. How? How do you see it?
In the form of.
No? Do you know?
Electricity.
Kind of, not quite. So think about your lab last week. What you did last week is you excited the electrons by putting them in fire. You excited the electrons in the atoms that you had, and they jumped up a couple energy levels. And when they jumped back down, what did you see?
In the form of energy?
It's type of energy.
Kinetic energy?
Light. Remember when you were doing your lab, all those colors you produced were different wavelengths of light. So this is the guy who was like, hold on, these electrons can move. And when they move, they emit energy in the form of light. And he said an electron in an atom can move from one energy level to another energy level if the atom gains or loses energy. So when you put your sample last week, your metal ion sample, into fire, you added energy and those electrons jumped up. And then when they lost that energy, they would fall back down and you would see that color produced in that wavelength. So what he said is, okay, Ernest, you were close. Remember, Ernest said they're revolving. So we can call it kind of like a planetary model. They're revolving, but they're at specific energy levels. They're not all revolving in one area. Some are closer and then they get further and further out. And then after Niels Bohr, we get to this dude. Okay, these are two guys that worked together. Well, contemporarily, we'll say, not necessarily together, but in the same time, they definitely, consulted with each other. So now we're in 1926. So we have Erwin Schrödinger and Werner Heisenberg. And the model is a way, they have what's called your electron cloud model. Okay, now this one is the hardest to visualize, but the most accurate, of course, right? It's always going to be hard to visualize if it's accurate. So anyway, the model was a way to visualize the most probable position of electrons in an atom. So the electron cloud model is currently what we know, and we also have another name for it. Do you know what it's called?
Electron cloud model?
No, another name for it. Do you know? Yes.
Atom model.
It's called the quantum model. So this is like, come on, click. Hello. There you go. Quantum mechanical model. You ever heard the term quantum mechanics? Yeah, there's some very, 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 very smart scientists who work in quantum mechanics. It is very complex field, but it's fascinating. And these guys are like, if you want to know about some geeky stuff, quantum mechanics is the route for you, let me tell you. So these guys are really hardworking, really smart guys. There's a lot of math. There's a lot of modeling, all that kind of stuff. So that's a quantum mechanical model, and it's the most accurate. Now, the reason he's got a little cat in his box here is because Erwin Schrödinger also did a lot of thought experiments with people, like just try and make you think. So he had an experiment called Schrodinger's cat. And the idea was that there's a cat in a box and something, I think there was like, he had it set up. So basically there was a way that the cat could be poisoned inside the box. So the question is the cat still alive or is the cat dead based on whether the box is open or closed? It's a complex concept, but it's supposed to make you really think. And it's an interesting one. So he's most famous, probably most people know if you say Schrodinger, the people are like, oh, Schrodinger's cat, because they've heard of that. Okay. And then Heisenberg, I did up here in this funny little wanted poster, because there used to be this television show. It's finished now, it's wrapped up. It was called Breaking Bad. You ever heard of Breaking Bad? Anybody ever heard of it? Okay. So the main character on that show is a chemist, but the whole show is about he becomes an illegal drug dealer, but somehow, which is not a good thing, but somehow he's also the protagonist in your story. He's the good guy, even though he's doing not so good things. But anyway, he, in order to stay anonymous, he picks a name for himself. And the name he picks is Heisenberg, because Werner Heisenberg is a very famous chemist. And he has some theories that go to him that are named for him. And so he chose that name. But that is what AI did when I asked it to take the wanted poster of Walter White from Breaking Bad and make it into a rat. And it actually, so it's kind of crazy that it did it. All right. So here we are again through time. We have Democritus that claimed that matter was made of small particles that he called atoms, and he proposed that it could not be divided into smaller pieces. Then we had Dalton come along. He created the first atomic theory, and he viewed atoms, as tiny solid balls. Then we had J.J. Thomson, and he showed that the atom was made of even smaller things. And it was known as, see, this says raisin bun. Really, it's plum pudding. That's probably the most accurate. But I guess whoever made this one decided for raisin bun. Then we had Rutherford, and he showed that atoms have positive particles in the center and that they're mostly empty space, which is true. And he discovered protons in the nucleus. Then we have Bohr, and for whatever reason,
Like a Simpson.
he is a Simpsons character
Yeah,
in this case. So obviously Niels Bohr was at some point featured on The Simpsons, and whoever made this graphic stole that image. You can find Niels Bohr represented in what was the movie that came out about the atomic bomb last year? Oh my gosh. Oppenheimer, yes. Oppenheimer, who is another very famous scientist. So Niels Bohr is in that Oppenheimer movie. And he's actually one of those people that, like, if you look at pictures of him from when he's young to pictures 20 years later, he didn't change. He's like one of those freaky people that doesn't age, like Pharrell Williams doesn't age. So that's Bohr. And he said that electrons moved around the nucleus, yes, but that they were in specific layers. Rutherford and Bohr were contemporaries. They worked together. And Rutherford learned from Thomson. So Thomson was Rutherford's teacher. Rutherford and Bohr worked together. We also had this guy Chadwick, and we didn't talk about him, but he's the one who discovered neutrons. We knew all the way back here with Rutherford that there were positive particles. And then if we knew that they had no charge, there must also be negative particles, right? Because if there's a positive, there has to be a negative to cancel it out. So otherwise they'd be charged. Everything would be charged. So he's the one that found that there were neutrons there. He worked with Rutherford. So these guys are all contemporaries, and they discovered particles with no charge, and he called them neutrons. And our modern theory since the 1920s is what we call the quantum mechanic theory, or the electron cloud model. All right, so look at that little atom there. So you have a nucleus, and then you have your electrons, and they're whizzing around at energy levels. Now, I just said something a minute ago. An atom is mostly empty space. What are you made of? Yeah. Thereby, what are you made of?
Protons.
You're made of atoms, right?
Yeah, so you're made of protons, neutrons, and
But an atom is mostly quote unquote empty space. So what are you mostly?
empty.
Oh, you ever thought about that?
Yeah,
Oh,
How's that?
one tiny speck of dust is equal to like billions of atoms, so that means like even if you got like a googolplexian atoms, it still would equal something very small probably.
So it's really interesting, but if you think about it critically, you are mostly empty space. What does that even mean? Because we don't even really know what empty space is, because empty space is usually like a vacuum, right? Like you think of like a black hole or a vacuum, or so there's no matter in there. But that's all the matter you are. See how much of that is not matter? See how much of that space is not matter? What is it? You're made of it. What is it? This is when you get into like dark matter and a couple of other similar theories. So it's very interesting. All right, so here we're going to take an example. We're taking argon. Where's argon? You see it? What is it, Eunice?
It's AR.
Yeah, what color is it on here?
Blue.
Yep,
Light blue, light
right
blue.
here. Okay, these are our noble gases, okay? Number one, we call these our noble gases over here. These guys don't interact with anything. They're called inert. All right, they don't mess around with anybody else. They don't like to react with anything. They just kind of chill out over here on their own. So they're helium, neon, argon, krypton, xenon, and radon.
Okay. So with the model, like, you can see the little symbols that say proton and neutron
Yeah.
and electron, but like, the plus sign is on like what color the neutrons are supposed to be, and the
Oh,
protons don't have.
you know, I think you're right. I think whoever made this did that like that. I think you're right. Maybe they're supposed to flip flop those. That's interesting. Those colors are very, those colors are very similar too. But what I want you to notice here is you've got your, oh, on my computer, it's far less obvious. It's real obvious on the screen. Oh yeah. It's not, they're barely different on my screen, but they're very different up here. So you see these little green rings? So those are your energy levels, and it shows you kind of where the electrons are with relationship to the nucleus. They get further away. How many electrons are in that first shell, that first ring? How many do we see there? We see two, right? And actually you can't fit more than two there, okay? And then in the next one, we got 1, 2, 3, 4, 5, 6, 7, 8. And that's actually all that can fit in that level. Right? Can't fit any more in that level. And then they keep going out from there, okay? But they don't actually look like that. That looks like a solar system kind of, right? They don't actually look like that. They actually look more like a cloud, and we'll get to it in a second. But this is a simple way of going, okay, I understand how far from the nucleus each of these electrons is. All right. So when we talk about charge of the particles and mass of the particles. So here's your proton. It's got a positive charge. And this is its actual mass in grams, 1.67 times 10 to the negative 24. That's a lot of zeros behind your decimal, okay? But what we use to talk about mass with subatomic particles is we use AMU, which is atomic mass unit. It's so much easier to just give them, yeah. And you see how like these basically have the same mass. And this one is way smaller. Just those four, the difference between negative 24 and negative 28 is huge, because negative 24 is 24 zeros, 28 zeros is much, much smaller, right? So this makes it so that when we talk about mass with atoms, we don't give a mass to electrons. They do have a mass, but it's itty bitty. So we don't consider them because it really doesn't contribute to the mass in a meaningful way with the type of reactions we'll be doing. But what we do is we assign this 1.67 times 10 to the negative 4. We assign it as 1 atomic mass unit for protons and 1 atomic mass unit for neutrons. And in actuality, neutrons are a tiny bit more, they have a tiny bit more mass. They're a little heavier, just a little heavier than protons. But we don't count a mass for electrons, just protons and neutrons. So what are our particles again? What's the positively charged particle called? Emerson? There's your protons. Okay, they are positively charged and they're in the nucleus. And what are the negatively charged ones that are found outside? Everly? Electrons. And then what are the neutral ones found in the nucleus? Emerson? Neutrons. There they are. Okay. So let's have a look at them up close. And really, it's more complicated for sure, because there are actually other particles kind of within those particles. We won't deal with these in chemistry. We don't even deal with these in high school chemistry. You get into quantum mechanics and stuff, you'll be doing these. But we have things called leptons and quarks, and they're even smaller, and they have partial charges, some of them. Like, see, this one says negative 1/3 of a charge. So this is like, if you really want to do quantum mechanics, this is your jam right here. And this is what I mean by the orbitals don't look like that solar system we just saw. They actually have really interesting shapes. So we talk about the quantum model. Remember back when we mentioned it the first time, I said it's the probability of finding an electron. Do you know what probability is? Do you know what that means? Like, what's that mean?
How likely something.
That's exactly
is to
right.
happen.
How likely? All right, so if you were to look for the first electron shell, and you were like, all right, I want to know where to find the electrons in the first energy layer. Where am I likely to find them? You're likely to find them within that red sphere. Okay, that's probably where they're going to be. It's a sphere. But if you're looking at the next energy level, it's kind of like a dumbbell or an hourglass. You see that? But here's the thing. These are layered on top of each other. So if you have an atom that has an electron in one of these yellow orbitals, it also has electrons in the red orbitals. So it's that on top of that, or the red one inside of the yellow one. And then it continues to go out and they get these really weird shapes, but that's where you're likely to find it. So you see why they call it a cloud now? Yeah. So let's look at each of these. They're distinguished by mass, charge, and location, protons, neutrons, and electrons. So we look at them comparatively. Our protons, there's our 1 AMU, which is 1.67 to the negative 22nd kilogram. And then we have
Charge is a plus.
its charge is a plus, and
Its location is in
nucleus. Very good. So this next one is neutrons. Now, what was its mass? Do we remember?
7 times 10 power.
Yeah, or
one
1 AMU, right?
More than 1 AMU.
Right. Okay. And then what's its charge?
0.
No, no charge at all. And then what's its location? In the nucleus. All right. So the last one's got to be our electrons. And what was there?
9.11 times 10
Yeah.
and 10 power negative.
So if you look, there's the AMU for it, 0.000548. So when we're doing math and we're trying to determine the mass of atoms, we don't even mess with the electrons, and that's why. Itty tiny by comparison. All right, and then what's the charge for an electron?
Negative.
Negative, and where are they found?
It's found in the outer part.
Outside, right?
Okay.
There you go. All right, now, if you look at lithium, okay, there's a number 3 here. Do we know what that 3 means? Do you know what it is?
It means like for hydrogen, it has like less AMUs, and then helium goes more, and then it's
Right.
like
So that number is going to be this little number here. So this 3 is the number of protons. That's our atomic number. We're going to talk about it more in a minute. But that is the number of protons. And this number is your number of
AMU.
protons, neutrons. We don't really weigh the electrons in, right? I mean, kind of we do, but not really. So what you find with a lot of these is that this number is going to be roughly twice this number, because usually you have the same number of neutrons as protons unless it's an isotope. And this number here, and also these AMUs, what they use is the most common, an average of the isotopes. So there's a little more that goes into it, but you'll find pattern wise, it's roughly twice. Yeah.
I'm just having trouble finding like the bigger picture of the periodic.
It should be right at the back of your preface.
Okay.
I think it's the last page of your preface. So if you look way at the front, and way up here, should be.
Oh, thank you.
Yep. And you have a small one on the back of your binder too, I think. All right, so here's what I was just saying. So atoms of different elements have a different number of protons. So what is equal to the number of protons in the element? This thing right here. What do we call this number? Do you know what it's called?
It's called
Everly? That's atomic number. Very good. That is the number of protons. That, listen, this is important. The number of protons determines what the atom is. Not the number of electrons, not the number of neutrons, always the number of protons. So if it has 7 protons, it's nitrogen. Don't care how many electrons, don't care how many neutrons. If it has 28 protons, it's nickel. Don't care how many electrons, don't care how many neutrons, all right? It's always that number. So what do we call the sum of all the protons and neutrons?
The atomic mass.
That, or mass number. You can call it either atomic mass or mass number. Okay, either of those is okay. And do you see that this is roughly twice that?
Yeah, 6
Right?
times 2 is roughly.
Yes, 6 times 2 is 12. This is roughly 12, right? That's what you're gonna see again and again and again,
So
okay?
you round it up.
Yeah, you don't, sometimes, not necessarily, but it should be close to twice, right? So like, when you get bigger, when they get bigger, they become less likely to be close to twice, because now you're adding in like, the very greater quantity of isotopes and that kind of thing, and then you have like little electron masses and stuff, yeah.
I just have a question, like how come in both of this periodic table and that periodic table, under yttrium, there are 2 blank spaces?
Are you talking right here?
Yeah?
Okay, so we're gonna look at this in just a second, all right? So hold on, we're gonna get there. So atomic number versus mass number. All right, atomic number is the number of protons, like we said, located, and it's located, sorry, at the top of the square in the periodic table. Hydrogen has an atomic number of what? 1, everybody, 1. Mass number is the sum of the protons and neutrons in the nucleus of an atom. So you can use the mass number as the only way to find the number of neutrons. Okay, and here's why. So this is what we were just saying. 30. Was a good example. But let's just look at the carbon that we looked at a second ago. So why isn't it exactly 12? Why isn't it exactly 12?
Because you add up the neutrons, and neutrons is a little more than the protons.
It's a little heavier, yep. That's
Yeah.
part of it. It's a little heavier. The other part of it is they actually get that neutron number. They don't take a perfect carbon atom and say, in a perfect carbon atom, it's gonna have 6 neutrons and 6 protons. There are actually carbon atoms that have a different number of, a different mass number because they have a different number of neutrons. That's called an isotope. That's common with a lot of different elements. And they take the average of the isotopes found in nature when they put that atomic mass on. So it's not exactly double, and that's why. All right. So isotopes, here they are, isotopes of carbon. Isotopes of an element have the same atomic number, but a different mass number because they have a different number of what? What'd I just say? A different number of, Lucy, you with us? Annabelle, what is it?
Electrons,
Not electrons.
protons.
Emerson? They have a different mass. Why? They have a different number of
Neutrons.
neutrons. Okay, different number of neutrons. So these are carbon isotopes, and these are real important because we actually use these when we date things like dinosaur bones, for example. We can tell how old something is based on what isotopes are present, because some isotopes is more complicated, but over time they decay, they change, and we know how many to expect, and we know how long it takes them to decay and change, and we can use that information to decide how old something is. So your run-of-the-mill pure carbon atom is going to have 6 protons, 6 neutrons, 6 electrons, but there are carbon-13 isotopes. It's called 13 because it has 7 neutrons. So now what's your atomic mass?
13.
13, right? Because it's 6 protons plus 7 neutrons. 6 plus 7 is 13. Carbon-14 has 6 protons, 8 neutrons.
14.
So it's 14.
And the 6, 8, 6
Mhm.
one is 20.
No, it's 14. 6 plus 8 is 14.
It's only neutrons plus electrons.
Yeah, we don't add the electrons in at all, right? So we leave the electrons out of the equation. See that the 6 electrons stayed the whole time. So isotopes have a different number of neutrons. Now later we're gonna have another I word, and it's ion. And ions have a different number of electrons. Okay, so but isotopes have a different number of neutrons. All right, patterns. So here's your question, Annabelle. We'll get to that in just a minute about why is there a hole there. So we have this dude. All right, this is our buddy, Dmitry Mendeleev. Okay, he was born in 1865. He's the guy we can credit with the birth of this type of organization. All right, so he expanded on an idea by this guy before him named Newland. Sorry. And they had already given symbols to certain atoms, like the symbol. These are symbols, B, C, N, O, F. They're already given symbols. So what he did is he put all of them on cards and he wrote the properties that he knew, including the masses, the number of protons, things like that. He wrote them out on cards, physical cards, and then he started trying to arrange them in a way that made sense. So as he began to teach inorganic chemistry is basic physical chemistry that doesn't involve organic compounds, which are things that contain carbon and come from living things like wood or bone or any of your proteins or any of that kind of stuff. So Mendeleev could not find a textbook that met his needs. Since he had already published a textbook in organic chemistry in 1861 and had been awarded the prestigious Demidov Prize, he set out to write another one. So as the result was this one called Osnovi Chemii, Principles of Chemistry. He's Russian, by the way, that's what these words are, which became a classic running through many editions and many translations. When Mendeleev began to compose the chapter on halogen elements, these are your halogens, fluorine, chlorine, bromine, iodine, right? So when he started working on the halogen, chlorine and its analogs, what we call these, all right? At the end of the first volume, he compared the properties of this group of elements to those in the group of alkali metals, such as sodium. Okay, where's sodium in here? Does anybody know where sodium is? You know?
It is Na.
Yeah, where is it?
Right there, the
Here.
red one.
So he was comparing this group that we have in red to this group that we have over here in green. Okay? Within these two groups of dissimilar elements, he discovered similarities in the progression of their atomic weights or masses. And he wondered if other groups of elements exhibited similar properties. So after studying the alkaline earth metals, those orange ones right there, okay, he established an order of atomic weights that could be used to not only arrange the elements within each group, but also arrange the groups themselves. Thus, in an effort to make sense of the extensive knowledge that already existed of the chemical and physical properties of chemical elements and their compounds. So he discovered what we call periodic law. Period meaning something that repeats in a pattern. Periodic law is saying that the patterns repeat predictably, okay? Now so he's a cool Russian dude. He's one of my favorite guys. He's got an amazing life story. So his first tables actually look like that. Okay, first off, that's written in Cyrillic, which is Russian language. So we write, our symbols are Arabic, you know, numbers are Arabic. Anyway, Roman. But he wrote in Cyrillic, so that's why it looks kind of funky. But you can see what he's doing, right? He's starting to arrange things. He's looking for patterns. He's making data tables, essentially, right? And that's how they looked at first. So what's not to love about this guy? All right. A lot, but we can start with some cool quotes. So now I'm going to try to endear Mendeleev to you. All right. This is why this guy's cool. So here's a quote from Mendeleev. The establishment of a law, meaning like this pattern, right? Moreover, does not take place when the first thought of it takes form, or even when its significance is recognized, but only when it has been confirmed by the results of the experiment. So you can't just decide there's a law. This is a law, ta-da. And you can't just say, oh, everybody else sees it too. Oh yeah, I see it. You're right, there's a law. You have to confirm it, he's saying, through a series of experiments.
Is it Dimitra?
Nope, that's the Russian spelling. There's no vowel there. There, you hear it in the syllable, Dimitri, there's obviously a vowel there, but there's not. When we drove through a lot of these, like, Russian and Slovakian stuff. My husband and I drove through the country of Slovakia once on a European vacation, and there was a town there named Brno. Bruno, Birno, Warno, Rhino. I have no idea because there are no vowels until the end. But apparently it's Bruno, but I don't know how you're supposed to know that. Give your sister a little room there, Emerson. All right. He also said work. Look for peace and calm in work. You will find it nowhere else. Basically, don't sit on your butt and do nothing. Find a vocation and do it. You will find satisfaction, peace and calm. That's what he's saying. He also said there's no talent, neither genius, without hard work. Mm-hmm.
Are we about to start the lab soon?
We got about 10 minutes.
Okay.
So he's big on working. This is also very Russian of him. They like working, hard working, right? He said, the most penetrating spirit before which will open the possibility of tilting not tables but planets is the spirit of free human inquiry. Believe only in that, meaning ask yourself big questions and try to get the answers. And also he's got these eyes, man. Okay, so this is, there are amazing Mendeleev memes all over the internet, which focus on the fact that he looks like a creepy dude. I mean, is it just, this is a gentle picture of him. This is the most gentle picture of him you'll ever find. Usually he looks terrifying, right? Uh-huh.
The one on the right looks like a very old.
Does it look like your grandpa? Well, I'd rather the one on the left be my grandpa. He looks a little kinder, right? Uh-huh.
Yeah,
Yeah,
that
that
looks
looks
like Einstein when he got into like the hundreds.
Okay. So these piercing eyes lead to even more cool quotes. And here are some of the fun quotes. My favorite element, surprise, stabs interviewer. Obviously that's fake science, but this is the kind of meme you can find about Mendeleev, because doesn't he looks like somebody who would stab an interviewer, doesn't he? He's got some piercing, scary eyes. But seriously, in 1850, Dmitry Mendeleev walked almost 1,000 miles, walked people on his feet in 1850s shoes, which are not the shoes you're wearing, I promise you that, walked 1,000 miles so he could apply to the University of Moscow. And he wasn't even accepted. So then he walked to St. Petersburg, not nearby necessarily, where he was accepted. And with that education, he developed periodic table. He was the youngest of 17 siblings. He had 16 brothers and sisters, of whom only 14 stayed alive long enough to be baptized, which they did pretty young in the Orthodox Church. So most of them lived past infancy at least, but at least 3 of them, to our knowledge, passed away before they were even old enough to get baptized. So within the first couple of days or weeks.
Mostly,
A lot of people died like that in the 1850s. It was risky. Yeah.
mostly the youngest of like a whole entire family become like a scientist.
Yeah, sometimes. Uh-huh.
You know that WTF stands for what?
Yeah, I do. Uh-huh.
Yeah.
What the frick? We can say that. So according to Mendeleev's brother Pavel, meaning the others died soon after their birth, right? That's what we were just saying. The exact number of his siblings differs from sources. Some say it was 16 or whatever, but we know it was a lot of siblings. So in 1876, he became obsessed with this girl named Anna Ivanova Popova. And he started courting her or flirting with her, right? Trying to get her attention. And in 1881, get this, pay attention. In 1881, he proposed to her and threatened suicide if she refused. If you don't marry me, I will kill myself. But this was all really interesting because he was still married to his wife, Lasheva. Yeah. So he was married to his wife, Lasheva. So that divorce was finalized a month after he married Anna. Fun guy. So even after the divorce, Mendeleev was technically a bigamist because their marriages overlapped by a month, which means that the Russian Orthodox Church required at least 7 years of lawful remarriage. So he's not in good standing with the church that is, and the Russian Orthodox Church was very involved in like the running of the country. It's not just like church separate from government. It's mixed in. So he was not in good favor for 7 years. This is why he was not admitted to the Russian Academy of Sciences, despite the fact that he's internationally famous, because the church was involved with the government and the church was not happy with him because he had 2 wives at once for a month. So he didn't get like the professional credit that he otherwise would have gotten, except for his personal problems. We're going to come back to that video. So here's your question about what's on the table, Annabelle. This is what you're asking. So the periodic table is divided into groups or columns. They go up and down, columns go vertically, like think about columns on a porch, they go vertically, or rows like in a theater, they go across, right? And it's divided into groups and periods. The groups are columns, the periods are rows, all right? Oops. So this little group down here, I was going to show you. There are a lot of elements, 57 through 71, that fit here, and they have been removed and placed down here so you can see them. Same thing here. So here are lanthanoids and actinoids. Technically, there's a way to make a periodic table out of paper that you can see it in 3 dimensions, so it kind of wraps around. but it's hard to see that on one
I
chart,
think
so
they put on
they removed them so that you can see them here, but they would fit technically there characteristic wise.
the periodic table would be audited.
Yeah, so let me go over this next bit with you and then we'll watch that quick video that I had. So next week is fall break, 9/24. So don't show up here. I will be in my pajamas. That's not what you want to see. All right, so I will be in my pajamas, no makeup, not looking great, don't show up. I'll scare you to death. You'll open the door and be like, ah! Right? So that's not happening. All right. So it's almost October. So what's that mean? All right, that means Tinker Day. Now let me just tell you about Tinker Day. Tinker Day is the best holiday. Tinker Day is a holiday celebrated at my college, okay? Hollins, all right? Now, here's what we do for Tinker Day. Whoops. It's fast approaching, so
We eat
prepare
donuts.
for donuts. If you can't have Krispy
Yum.
Kreme for some reason, let me know. Why donuts? Because that's what you do on Tinker Day. You get donuts and you get to climb a mountain. So Tinker Day happens once a year, every October at my college. The president of the college decides what day it's going to be, and she doesn't tell anyone. And then on that morning, you're awakened to the sound of the chapel bells ringing really loudly before class, like 6 a.m. Chapel bells are bing, 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 bing. And you know that means it's Tinker Day. And that's awesome because that means your classes are canceled. You get to play hooky with the whole school. And everybody's still in their jammies. Everybody marches down because it's a women's college, so we can all be in our pajamas. We don't care. We all march down to the cafeteria, and our breakfast is Krispy Kreme donuts. It has been Krispy Kreme donuts for decades. It is thousands of Krispy Kreme donuts. So you eat your Krispy Kreme donuts, and you can have eggs and bacon and whatever else too, but you eat your Krispy Kreme donuts. Then you go back to your dorm room, and you've been planning for weeks because you know this is coming. You have the most amazing costume prepared because you've been planning. You put on a wacky costume, and then you go back to the front quad and you wait. And then the president comes out and she reads this proclamation and she says, it's Tinker Day. And then you and everybody else, including the faculty, the staff, your professors, the people that work the grounds and mow the lawn, everybody walks off the campus, down back road, down another back road, and climbs a mountain. And when you get to the top of the mountain, they do skits, they sing songs, then we eat fried chicken, always fried chicken, and a special kind of cake called Tinker Cake that comes out on Tinker Day. That's it. And then you get to go back down the hill, and that's the day. That's the whole day. But this is crazy because, so I was saying,
What was Tinker
it's
Day?
the most amazing holiday of all time. So I just enlightened the newbies. Now, here's where it's a bonus point opportunity for you. Bonus points. All right, so these bonus points go for your midterm. So you want them, okay? Don't worry, I'll let you know when it is. I'm going to post in the forum and send out an announcement. Hold on, to tell you all it's Tinker Day, all right? And if Tinker Day should occur on a day other than a Tuesday, you can post a picture in the comments where I put it in the forum and I say, it's Tinker Day. You post a picture in the comments. If you get a picture of you eating a Krispy Kreme, it's 1 point. If you get a picture of you taking a hike, it's 1 point. If you get a picture of you dressed all wacky for Tinker Day, it's 1 point. And if you get a picture of you wearing green and gold, it's 1 point. So if you do one of these things, any one of these things, it's 1 point. But if you take a picture of yourself on top of a mountain, eating Krispy Kreme, wearing something wacky green and gold, and you snap it on Tinker Day, you have to take these pictures on Tinker Day. You can't take them another day. And you can prove you took it on Tinker Day. Like hold up your mom's phone next to it that has the date. Ta-da! You get 3 points on your midterm. That's big. That's added to your final score. And if it happens on a Tinker Day, if you wear green and gold to class, you get 1 point. If you wear something wacky green and gold, you get 2 points. So something wacky would be 2 points. Something wacky green and gold is 3 points. So here's why Tinker Day is awesome. Women at my college have been climbing the mountain since 1895. Look at this picture. You see what they're wearing? They climbed a mountain in those shoes, in those wool skirts. It's a big thing. It's a lot of fun. So we don't have time for that one video that I put in your slides, but I'll post it in the resources right at the end of your email and whatever, and you'll know where to find it. Did you have a question real quick? Yeah.
I don't like Krispy Kreme.
You don't like it?
Miss Danny?
What's wrong with you?
Miss Danny,
Yes.
I had a question.
Yes, what's your question?
So, when was Tinker Day invented?
In the 1890s. Been doing it for a very, very, very long time. Yep, say 1895, which means that my second Tinker Day was the 100th anniversary of Tinker Day. It was the 100th Tinker Day. It was pretty darn cool. Yep. All right.
What do you do on Tinker Day?
Well, that's up to you if you're at home, but